Hello, friends. Do you think of this Earth where we humans exist? Do you think of such an Earth that is inhabited and swarming with hundreds and thousands of species? Nevertheless, 4 billion years back, this very Earth was in fact molten lava. Nothing came there but a bright glow, a glowing sphere with a sea of fire. In itself, this makes very fascinating questions. How from molten mass turned Earth like that which lives within? Where was this water coming from? How did the moon come into existence? These questions are all tied to the birth of our sun and solar system. In this video, let's explore these questions in depth. Around 4.6 billion years ago, yes, 4.6 billion years ago, our solar system did not exist. Instead, there was just darkness, deep, silent, and empty space. Within this space was a cloud of gas and dust, known as the solar nebula, or Niharika in Hindi. This cloud primarily contained hydrogen and helium. For millions of years, this cloud drifted peacefully through space until, one day, a massive explosion occurred. And no, I'm not referring to the Big Bang. I'm talking about a supernova. A dying star exploded in a nearby location, generating waves that traveled to the solar nebula. Gravitational instability was thereby established, and in some parts of the cloud, the gas and dust compressed. Slowly, the entire nebula collapsed inwards, with gas and dust revolving around it. At this point, the nebula took the shape of a rotating disk, which is known as the proto-planetary disk. Proto means before, referring to the disk that existed before the planets were formed. As shown in the animation, this is what the disk looked like. Because of its flat shape, we can better understand why our solar system is also flat. As I explained in the Voyager video, the planets in our solar system orbit the sun in nearly the same plane, with their orbits aligned and not significantly higher or lower than each other. Now, at the center of this protoplanetary disk, the pressure and temperature kept increasing, leading to the formation of a protostar. A protostar is essentially what existed before the star itself was formed. Gradually, the gas and dust from the nebula were drawn toward the center due to rising temperature and pressure. Eventually, the center became so concentrated that nuclear fusion began, specifically the fusion of hydrogen. This reaction occurs at around 15 million degrees Celsius, turning hydrogen into helium. It's what led to the formation of our sun, and it is still in effect today, giving us all that light, heat, and energy we get from Earth. The details involved in the fusion process are very complicated, but at its core, it is very simple. Hydrogen turns into helium. Well, way back 4.6 billion years ago, most of the gas and dust in the solar nebula ended up in the sun. The sun now makes up about 99.8% of the total mass of our solar system. The remaining 0.2% became the planets, moons, comets, and asteroids in our solar system. So, how were these planets formed? Isn't that cool? These dust particles within the rotating protoplanetary disk started sticking to each other due to static electricity or chemical bonds, and thus started colliding. Small clusters began to form during the early stages, and over millions of years, collisions built more clusters up. Some got quite large. Their diameters ranged between 1,000 meters and a few kilometers. These bodies are called planetesimals, the small versions of planets. As gravity pulled these planetesimals together and their size increased to the size of our moon, they became protoplanets. This process of particles sticking together is known as accretion, which is defined as the coming together of matter under gravity to form larger bodies. It was Soviet astronomer Viktor Safronov who first came up with this process back in 1969, although his ideas were not quite well accepted until 1984. Today, using very powerful telescopes, scientists watch this process happening all over the universe. Astronomers have watched this process in other solar nebulae, where dust particles accumulate so fast that they grow up to about 1 centimeter within a few thousand years. Scientists now confidently say that after millions of years, those small particles eventually grew into planets. One of the main pieces of evidence is meteorites. When scientists study meteorites, they often find chondrules of small pieces of dust and rocks from before the planets formed. These contain radioactive elements like uranium and hafnium, which help scientists estimate their age. Interestingly, the uranium found on Earth is older than our solar system. about 6 billion years old. This uranium formed in a supernova. By collecting data from these meteorites, scientists can simulate the collisions of dust and planetesimals. These simulations suggest it took tens of millions of years for the protoplanets to form. Now let's talk about Earth. These small protoplanets and planetesimals crashed into each other frequently, and these were not the gentle bumps. The amount of energy produced was colossal, generating so much heat that it melted rocks to form seas of lava. As these protoplanets collided and grew, gravity forced them to become more spherical in shape. After many such collisions, Earth was formed over time. Over millions of years, gravity pulls these rocks together to form the Earth, one of at least 100 planets circling the Sun. During this time of constant collisions, small protoplanets and planetesimals collided with Earth regularly. This period is known as the Hadean Eon. The word eon refers to an indefinitely long period of time. The term Hadean comes from Hades, the Greek god of the underworld, and one can easily see why that would be. During this period, Earth looked pretty much like descriptions of hell. This time frame dates back from about 4.6 billion to 4 billion years ago. Some of the objects that collided with Earth during this time had diameters as large as 100 to 200 kilometers. Any rocks present on Earth at the time would have melted and been compressed into lava, then compressed again. But the cool part is that this horrific epoch was actually Earth's ice cube key. Water-encrusted comets and asteroids hit the planet. How did asteroids and comets contain water? They received it from the solar nebula, the dust and gas cloud I previously talked about, which contained ice crystals. Earth also possessed its own water. When the minerals trapped in those microscopic crystals of this period are analyzed, scientists found some evidence of liquid water on Earth. It was, however, the colliding asteroids and comets that doubled the Earth's water stock. At the same time, there was another critical process going on. During these impacts, water would evaporate into steam and move up into the air and eventually fall back to the Earth as rain. At the end of the Hadean Eon, Earth had become a homogeneous ball surrounded entirely by magma, forming a uniform layer of lava held together by gravity. This led to a process known as differentiation. You may wonder how sure we are that these occurred. There are a number of techniques that support these observations. For example, through radiometric dating, which involves analyzing ancient minerals' composition and age, scientists determine the timing of those processes. Another approach is comparative planetology, in which scientists study the material composition of other planets, thereby learning how they built up. Computer simulations will also help model these historical processes by using gases and elements of that time period. These simulations allow scientists to see and track how Earth might have evolved. We all know about Earth's three main layers: the crust, mantle, and core. By the end of the Hadean Eon, Earth's crust had started forming. However, these layers were not separated until the next period, the Archean Eon, which lasted from 4 billion to 2.5 billion years ago. At this time, the molten Earth began to differentiate, as heavier elements such as iron and nickel sank toward the center of the Earth under gravity, while lighter elements such as silicon, oxygen, and aluminum floated toward the surface. This differentiation process continued, and over millions of years, Earth's core began to take shape. The core, made of iron and nickel, is the hottest part of the planet, reaching temperatures of about 6,000 degrees Celsius. Normally, iron should melt at this temperature. However, the immense pressure in Earth's center doesn't let it melt, so iron is kept in solid form. Such high temperatures are also caused partially due to radioactive decay of elements, such as uranium, thorium, and potassium in the mantle. Mantle. It is the thickest layer of Earth, being approximately 3,000 kilometers in depth. During Archean Eon, it was filled with magma. As the lighter elements rose and cooled at the surface, they made up the crust. Of all the elements in the crust, oxygen was most abundant, accounting for 46% of its mass. Today, the types of rocks in the crust include granite, basalt, and metamorphic rocks, indicating the transition from the mantle to the crust. These rocks are characterized by forming under extreme pressure and temperature. For example, marble and slate. The process of differentiation continued to millions of years, creating Earth's layers. Although in school students are taught primarily about three major layers that make Earth, the interior of the Earth is really more complex. Depending upon physical properties, Earth is composed of 5 distinct layers, which include lithosphere, asthenosphere, mesospheric mantle, outer core, and inner core. The lithosphere is Earth's outermost layer comprising oceanic and continental crusts, the oceanic being thinner compared to the thickness of continental crust. This leads us to the tectonic plates, which are a part of the lithosphere. These are not in the form of a whole sheet, but rather broken pieces. Wherever these tectonic plates meet, volcanoes arise. If these plates move against each other, then the result is earthquakes. Underlying the lithosphere is asthenosphere, a moving layer which is considered to be the lubricant of the tectonic plates. The average thickness is about 140 kilometers. Deeper within the mantle, there is a transition zone where rocks become denser under high pressure. Minerals like olivine, peridotite, and ringwoodite are found here. These high-pressure minerals are brought to the surface by natural processes, offering us a glimpse into Earth's deeper layers. During volcanic eruptions, magma erupts from the volcano, carrying high-pressure minerals from the mantle. Similarly, when meteorites collide with Earth at high speeds, the pressure can also create these minerals. Moving inward, we reach the Earth's core. In the outer core, iron is constantly churning due to heat, generating electrical currents, as iron is a good conductor of electricity. These currents form a magnetic field, which is essential for sustaining life on Earth. The magnetic field protects us from harmful charged particles emitted by the sun, solar winds, and helps keep the atmosphere intact. The primary difference between the outer and inner core layers is that the outer core is liquid, while the inner core is solid. Interestingly, as the liquid in the outer core cools, it solidifies, causing the inner core to grow by about 1 millimeter each year. Now you might wonder how the moon formed. The answer lies in the Hadean eon. There were several theories, including the capture theory, which suggested that the moon was captured by Earth's gravitational force, and the co-formation theory, which claimed that the Earth and moon formed together. Another idea was the fission theory, suggesting part of Earth broke off to become the moon. However, most scientists now believe that the moon was formed after a giant collision with a protoplanet called Theia about 4.5 billion years ago. The collision fused both planets' cores and created a chunk of debris that later became the moon. Evidence for this theory came from the lunar samples that NASA's Apollo missions returned. Basaltic rocks in the moon's mantle were almost identical to those found on Earth, sharing the same oxygen isotopes and elements. It proved that the moon was basically a piece of Earth that had broken off violently rather than Earth breaking off itself. This collision also tilted Earth's axis by 23.5 degrees, which is essential for the seasons that we experience. Without such a tilt, there would be extreme climate conditions, and it would be hard to sustain life. Moreover, the gravitational pull of the moon on oceans causes tides, and this was one of the reasons why life transitioned from oceans to land. Returning to the Archean eon, after the separation of Earth's layers, volcanic activity was intense. Volcanoes released gases like water vapor, carbon dioxide, methane, and ammonia into the atmosphere, which were toxic due to the lack of oxygen. Over time, as the Earth cooled, water vapor condensed and rained down, forming large oceans. This was also influenced by the impact of asteroids and comets, which contributed to Earth's water supply. These oceans played a crucial role in Earth's climate, absorbing carbon dioxide and heat, making temperatures more amenable to life. The interesting thing is that even today, oceans absorb most of the carbon dioxide produced by human activities, though their capacity is gradually diminishing. The events I discussed contributed to the emergence of life. Earth had to be precisely positioned relative to the sun, the right size for the magnetic field and all that volcanic activity to put everything in place for life. It just doesn't happen very often. That's why we haven't found alien life yet. But we all have to try to protect this planet. If you are interested in learning more about Earth's evolution, then watch my video on human evolution. Thanks.